Hey, it's Krish, and this is part 2 in my series of creating a plasmid capable of curing breast cancer. In the first episode, we created a custom plasmid capable of tumor suppression. But this is only part of the equation, as we still need to find a way of actually inserting our plasmid into the human genome. One of the ways we can do this is by leveraging CRISPR. However, to use CRISPR, we actually identify a couple of components. Firstly being the spacer RNA, or the sequence that we're actually inserting into the genome. In our case, this is the plasmid we created in the last episode, so we don't actually have to worry about this. The second component is the guide RNA, which is a molecule that tells us where our actual sequence is going to be located inside the genome. In today's episode, we're going to create a guide RNA for our plasmid. We've actually left off exactly where we were in the last episode, so you guys can easily follow along. Firstly, we have to pick a gene to insert our plasmid into, and the gene we've chosen is CDK2NA. This gene is a member of the alpha interferon gene cluster on chromosome 9, and is activated in response to a viral infection as part of the immune response. And we know that CDK already serves a prevalent role in tumor suppression, so by inserting our plasmid into the genome, we're going to give it a huge boost. In reality, this will make the spread of cancer significantly slower, rather than cure it altogether, but it's probably going to allow doctors to make a diagnosis while the tumor is still in its early stages with less critical symptoms. So we're going to start by actually importing a CRISPR guide. So if you go over here and press CRISPR, and press CRISPR guides, and now we have to actually search for the CDK2NA gene. So its ID is actually on screen right now, and it's also in the description, and it's going to be this, and there you go, CDK2NA. And for this one, we actually have to go to the advanced settings, and the reason is we have to look up all the transcripts and exons. We want to target as many transcripts and exons as possible to maximize effectiveness. The exons essentially act as binding sites for the guide RNA, and thus with more binding sites that are available, the lesser the probability is to miss. One exon has roughly 1 to 5 binding sites throughout the gene, with each gene almost having a dozen or more exons. So to highlight this, depending on what computer you have, all you have to do is to go to the top and press Ctrl-A or Command-A, and it's going to highlight all the different exons. Just verify, make sure that it's all highlighted, and then we're going to press Next. And then after pressing Next, it's going to bring you to a second window, which we don't have to add anything here, we just press Finish. And there you go, this is the map for the CRISPR guide. So in the linear map, you can see where all the exons are located, and we want to target the most number of exons as possible. So I think we're going to go with this region over here, so we can just quickly zoom in. There we go. Yeah, so you can see this region encompasses most of the exons, and when we go to the Design CRISPR tab, it's going to say that we need a specific target region. So for our guide RNA, we're going to have the target region be this exon right here, as it encompasses all the other different exons. And then we go to Design CRISPR, and there you go. Benchling has already automatically filled out the specific bases that the target region encompasses. So we just press Create, and it's going to give us a list of all the guides, as well as the on-target and off-target scores. In essence, the higher the score for on-target, the better the plasmid will function, and the higher the score for off-target, the less damage it's going to cause if it goes awry. Therefore, the scores explain the theoretical success of the guide, and we want both values to be close to 100 as possible. Usually we pick 1 to 3 guides to ensure success in knocking in the gene, as all the various different guides have different levels of efficiency. To do this, we're just going to make sure that we have a good balance between both scores, so we can sort by largest. So this one is a very solid score, has 70 and 40, so we're going to pick this as 1. We can also pick this is a very good score as well. And then for the last one, we can play around with a couple of them. This would be a pretty good one. This would be a pretty good one as well. Keep going. See, this one would not be a good one because it only encompasses 2 of them, and we want to make sure that we get all of them. So we can go up a little bit. This one's, I think we're gonna go with this one. This one's very solid. It has a good score a very good balance between both, and it encompasses all the various different exons. So all we have to do is simply right-click on the recognition site to copy. So there we go, and we can just copy. There you go. And it's going to give us a sequence. And once we've derived the necessary guide RNA, we can assemble it in a wet lab. And this is done by adding the recognition site to the guide RNA and then inserting the plasmid that we created as a spacer DNA. Since we selected a single-stranded CRISPR, what the Cas protein is going to do is going to make a cut on one strand, and the DNA polymerase will fill in the complementary strand. And that's it. We've successfully created a plasmid capable of suppressing a tumor and removing various harmful side effects, as well as enhancing diagnostic capabilities with the help of a selection marker. Of course, our plasmid will only work in theory, and further refining and testing is needed before human trials. But who knows? Maybe one day scientists will use our plasmid to cure cancer. I've linked the entire Benchling project down below in the description, so if you guys want, check it out. And it's been a pleasure working with you guys. Krish out.